So that's easy to understand. What seems to be harder to understand is that if the map goes below, it's again true that this can be an interval. And I'll try to illustrate this by the 3 cycles. What happens when you go below is that these cycles get closer and closer to each other. At some point, you lose them. Now, how are you going to lose those cycles? In Dike map, it's very easy to understand how you lose cycles. You take scissors or a knife and you cut the tip of this thing. That plays the same role as cutting this hole, but now it's below 1 rather than above 1. Now, if you cut it above, you can see that these things are ordered relative to each other. So 1, 0, 0 is further out than 0, 1, 1, just because that's how the intervals that I visit are ordered. So as I lower this, at some point, I'll get to the value where my so-called needing value, which is the symbol sequence converted to coordinate for the 10th map, needing value coincides with 0, 1, 0. And if I go below, I'll lose that cycle. But I won't lose the other one, because the other one, there'll be a whole interval of the values for which this happens. So what's going on? It's totally apparent because this belongs to that interval, because we have spatial ordering. That's why we have spatial ordering. So we are guaranteed. And we are guaranteed there is a whole interval of the values in between, finite interval, roughly side 1/8 of the whole thing, roughly speaking. So what happens for unimodal map that's doing this? So let's now look at parabola first to motivate why we use Dike map. I computed this for a equals 1.76, some parabola parameter. And now what happens is my parabola doesn't quite reach the ceiling. In this notation, it would reach ceiling at 2. So it looks like that. And if you look carefully at what's going on, is this first cycle, the one with symbolic dynamics 0, 1, 0, this first cycle, has a property that one of its points, this one, called 0, 1, 0, has gone into the region close to the critical point. Now at critical point, slope is approaching 0. See, here slope is, let's say, of order 3. Here the slope is maybe minus 3.5. And the Jacobian of the orbit, this is one-dimensional map, so Jacobian is 1-by-1 matrix. It's a product of these 3 derivatives. One of them evaluated at 0, 1. The other one at the next point, 0, 1, 0. The third one, 1, 0, 0. And now what's happening, this guy can be arbitrarily small. If I adjust it in such a way that it coincides with critical point, then its slope is exactly 0. That's called a superstable cycle. There's a whole interval range of inter A, meaning I can move this a little while in such a way that this is a stable cycle. What does that mean? That means a stable cycle has a finite basin of attraction. So a stable cycle owns a whole interval around it. So if I start any place in this interval, which I call C, I fall into the hole, and the hole is an attractive 3 cycle. attractive three-cycle is not just a point, it owns a whole interval around it, where everybody falls into that. So this is a basin of attraction. What happens to the other stuff? This basin of attraction has two preimages. So everybody in this interval, in one iteration, falls into immediate basin of attraction, and then it approaches the three-cycle. There is a whole open interval here, and there is a whole open interval here of points which iterated twice. So this interval here, call it 0C, and whole interval call MC0, which in two iterations, well, in one iteration ends in here. There is an open interval of points where I end up in this three-cycle. This is very similar to what happened here, except in this case my attractor was at infinity, and in this case my attractor is embedded within the map. So in here there is this attractive cycle, and I can make it fat, saying that it owns the whole neighborhood around it. There's a whole neighborhood of points which all are owned by the three-cycle. What happened to all other unstable points? We used to have infinitely many cycles of arbitrary length. Where did they go? Well, they still exist. So there is a counter set of points. After I removed all preimages of three-cycle, there is a remainder, which turns out to be counter set because I'm removing finite intervals. And in it reside all admissible orbits. And now they have the same role as they had there. If I am close to them, I have, for a long time, I can stay in their neighborhood, but it's a transient neighborhood. So if I perturb them, I always end up in a three-cycle. Just like here, I had all 2 to the n periodic points of length n, but if I perturb any one of them, I would escape, because they form a thin set of unstable points. Our dynamics has now divided into two parts. There is an attracting cycle, and there is a complement of it, and complement is very rich, and it's going to describe transient dynamics of falling into that cycle. So now what that means, this is much clearer when you now look at the Dike map. So Dike map is designed to capture this behavior, saying that there are values between this cycle and that cycle, so I can cut the Dike map, and if I cut it someplace here, what will happen is this will actually be a super stable three-cycle. See, if I iterate this, I end up there, go there, there, and I end up in this thing. So there'll be a whole range of kappa values. So the needing values, kappa, coordinates for this map, our model map for all unimodal maps, the simplest one, canonical one. If I'm in this interval, starting with kappa of this map, 0, 1, 0, which I know how to compute, kappa to kappa of 0, 1, 1, I will have a super stable three-stack. And if I lower my kappa below that value, then I've lost all three cycles. I know that I don't have a three-cycle anymore. I might have longer cycles, but this one I don't have. So the main message is, think of critical point not as just some point you can ignore. There are three kinds of behaviors. Either you are in the complement of that critical point, so your dynamics doesn't visit it. And that gives you all orbits which avoid either escaping or falling into a stable cycle. And then there are sequences in which you replace one of these letters by C because you end up in this interval. So you wander around and you end up in this interval, wander around. And if you compute the stability of the cycle, because whenever you end up here, we have designed it so the slope is 0, so it's super stable. But it's modeling all maps which have stability of the cycle, open intervals. So the critical point is not a point, it's an interval in general. And then you can discuss the parameter values for which you never end up in a periodic orbits, etc. So you can discuss which fraction of initial maps the parameter values. Now,